Welcome to this coding walkthrough. In this session, we'll tackle a popular problem, problem number 286, walls and gates. This problem challenges us to work with grids and find optimal paths to solve a practical spatial problem. Stay tuned as we break it down step by step and explore different approaches. In this problem, you are working with a 2D grid that represents a layout of rooms. Each cell in the grid will contain one of three possible values. A value of -1 indicates a wall or obstacle, which cannot be passed through. A value of 0 represents a gate, which serves as the starting point for calculating distances. Finally, the value 2147483647, which is equivalent to 2-31-1, represents an empty room. Your task is to update the grid in place by replacing the value of each empty room with the shortest distance to the nearest gate. If no gate is reachable from an empty room, its value should remain as 2147483647. It's important to note that the distance is measured by moving only in the four cardinal directions up, down, left, and right, so diagonal movement is not allowed. Let's look at an example to understand how this works. Imagine we are given the following grid: 214-748-3647, -1, 0, 214-748-3647, 214-748-3647, 214-748-3647, 214-748-3647, -1, 214-748-3647, -1, 214-748-3647, -1, 0, -1, 214-748-3647, 214-748-3647. Here, the task is to determine the shortest distance from each empty room, represented by 214-748-3647, to its nearest gate, represented by 0. After processing the grid, the output would look like this: 3, -1, 0, 1, 2, 2, 1, -1, 1, -1, 2, -1, 0, -1, 3, 4. Each number in the resulting grid represents the shortest distance from that cell to the nearest gate, while walls remain unchanged at -1. Here's an explanation of how the distances are calculated in the first example. Starting from the gates, which are the cells with the value 0, we calculate the distance to the nearest gate for every empty room. For instance, the cell at position rooms 0, 0 has a distance of 3. You can reach the cell by moving down twice and then right once to get to the gate at rooms 3, 0. Similarly, the cell at rooms 1, 2 has a distance of 1 because it is directly above the gate at rooms 2, 2. Now consider a second example. If the input grid is 0, 214-748-3647, 214-748-3647, -1, -1, 214-748-3647, 214-748-3647, 0, -1, the output will be 0, 1, 2, -1, -1, 3, 1, 0, -1. Again, distances are calculated from the gates to the empty rooms, while walls remain unchanged. Let's break down the explanation of the second example. The gate at position rooms 0, 0 propagates distances to the adjacent empty rooms, starting with rooms 0, 1, which is 1 step away, and then rooms 0, 2, which is 2 steps away. Similarly, the gate at position rooms 2, 1 propagates distances to its neighboring rooms. For example, rooms 2, 0 is just 1 step away from this gate. Notice that walls, represented by -1, block the propagation of distances. As a result, any room that is separated from all gates by walls will remain at its original value of 214-748-3647. Moving on to the constraints, the grid has dimensions of mxn, where m and n can range from 1 to 250. Each cell in the grid is guaranteed to contain one of the three valid values, -1, 0, or 214-748-3647. There may be any number of gates, including none at all, and the grid will always fit in memory. To solve this problem, it's important to modify the grid in place, meaning you'll update the original grid without using additional grids for storage. The most efficient way to propagate distances from gates to empty rooms is by using a breadth-first search, or BFS. BFS is ideal here because it ensures that each room is visited in the order of increasing distance from the nearest gate. This guarantees that when you update a room's distance, it is always the shortest possible distance. Additionally, BFS allows you to efficiently handle edge cases, such as handling grids with no gates, all walls, or single row and single column grids. By leveraging BFS, you can ensure that the solution is both correct and efficient for grids of any valid size. To solve the walls and gates problem, the brute force approach starts by iterating over every empty room, represented by the value 214, 748, 3647. For each of these rooms, we calculate the shortest distance to all gates, which are represented by the value 0. This is done using either a breadth-first search or depth-first search, initiated from each room. The idea is to traverse the grid to find the nearest gate for every single empty room. However, this approach is computationally expensive. Since the process involves performing a BFS or DFS for each empty room, the time complexity becomes O, m*n*, m plus n, where m and n are the dimensions of the grid. Additionally, the space complexity is O, m** n, due to the queue or recursion stack used during the search. The key drawback here is inefficiency. Many cells are visited multiple times for different rooms, leading to significant redundancy. While the brute force method is straightforward, it does not scale well for larger grids and is not practical for this problem. Now, a more efficient strategy is the optimized approach using multisource BFS. Instead of starting a BFS or DFS from every empty room, we reverse the perspective, start a BFS from all gates simultaneously and propagate distances outward. This way, each empty room is updated only once with its minimum distance to the nearest gate. The process begins by identifying all gates in the grid and adding their coordinates to a queue. Then, a BFS is performed from all these gates at the same time. When a cell is dequeued, its neighboring empty rooms are updated with the distance from the nearest gate, and those neighbors are added to the queue for further processing. This continues until all reachable empty rooms have been updated. The beauty of this approach lies in the nature of BFS, which calculates the shortest path in an unweighted grid by default. By starting from all gates simultaneously, we ensure that distances are updated in increasing order, avoiding redundant calculations. The time complexity is O, m** n, as each cell is processed only once, and the space complexity is O, m** n, for the BFS queue. This approach is both efficient and intuitive, making it a clear choice for solving the problem. When comparing the two approaches, the brute force method, while simple to implement, is computationally expensive and poorly suited for large grids due to its high time complexity. It involves repeated work and lacks scalability. On the other hand, the optimized BFS approach is highly efficient with its linear time complexity of O, m** n. Although it is slightly more complex to implement, the performance gains and reduced redundancy make it far superior. The chosen strategy, optimized BFS, represents the best balance between clarity, efficiency, and scalability. It ensures that each room is updated with its correct distance in constant time per cell, achieving optimal performance for the entire grid. This makes it the ideal solution for the walls and gates problem. In this problem, we're tasked with updating a 2D grid where each cell can either be a gate, a wall, or an empty room. Gates are marked with a value of 0, walls with -1, and empty rooms with the value 214, 748, 3647, which represents infinity. The objective is to calculate the shortest distance from each empty room to its nearest gate. If an empty room is unreachable from any gate, it should remain as 214, 748, 3647. To solve this efficiently, we use a technique called multisource BFS. This method allows us to treat all gates as starting points, and we simultaneously propagate their distances across the grid. BFS is particularly well suited here because it guarantees the shortest path in an unweighted grid. This ensures that we can update the grid accurately and efficiently while adhering to the problem's constraints, such as performing updates in place and considering the grid size of m by n. To implement this solution, we first initialize the necessary data structures. Specifically, we use a queue to store the coordinates of all gates. This queue will allow us to process the gates level by level during BFS. As we iterate through the grid, whenever we encounter a gate, we enqueue its coordinates and prepare to start BFS from these gates simultaneously. During the BFS process, for each gate, we dequeue a cell, and for all its valid neighbors, those that are within bounds and not walls, we check if the neighbor is an empty room. If it is, we update its value to represent the distance from the gate, calculated as the current cell's value plus 1. We then enqueue this neighbor into the queue to continue the propagation. This ensures that distances are updated systematically and correctly. Finally, we handle boundary conditions by ensuring all neighbors are valid grid cells, skipping walls or cells that have already been updated. The process terminates once all reachable empty rooms have been updated with their shortest distances. The key data structures we rely on here are the queue and the grid itself. The queue plays a central role in BFS, storing the coordinates of gates initially and then their neighbors as distances propagate. This FIFO structure ensures that cells are processed in the correct order, based on their proximity to the nearest gate. Meanwhile, the grid serves as both the input and the output. By performing updates directly on the grid, we avoid using additional memory, making the solution more efficient. The multi-source BFS approach is critical because it enables us to start from all gates simultaneously, ensuring that each empty room is updated with the shortest possible distance. This is far more efficient than a brute force approach where each empty room would be processed individually. The overall efficiency of this algorithm is notable, with a time complexity of O(m*(n), since each cell is processed only once, and a space complexity of O(g), where g is the number of gates, as this determines the maximum size of the queue. The intuition behind using BFS lies in its level-by-level exploration. As BFS progresses, it ensures that all cells at a given distance are fully processed before moving to the next level. This guarantees that when an empty room is visited for the first time, it is from the nearest gate. This property is crucial for solving the problem efficiently. There are also several edge cases to consider. If there are no gates in the grid, no distances can be propagated, so all empty rooms remain as 214, 748, 3647. If there are no empty rooms, the grid remains unchanged since there are no cells to update. Finally, if walls block paths, BFS naturally handles this by skipping walls, ensuring that invalid updates do not occur. To illustrate, consider an example grid. It contains gates, walls, and empty rooms in specific positions. By applying the algorithm, we can see how distances propagate from the gates, accounting for these edge cases. Let's break down the example grid step by step. First, we identify the gates and enqueue their coordinates. In this case, the gates are located at 0, 0, and 2, 1, so we add these positions to the queue. Next, we start BFS propagation from both gates simultaneously. For the gate at 0, 0, we process its neighbors. The neighbor at 1, 0 is an empty room, so we update its value to 1 and add it to the queue. Similarly, for the gate at 2, 1, we update its neighbor at 1, 1 to 1 and enqueue it. This process continues, with each cell updating its neighbors until all reachable empty rooms have been processed. The final grid shows the shortest distances from each empty room to the nearest gate, with walls and unreachable rooms unchanged. This step-by-step approach demonstrates how BFS systematically propagates distances while respecting the constraints of the problem. To summarize, the algorithm achieves optimal performance by leveraging multi-source BFS. The time complexity is O(m*(n), because each cell in the grid is processed at most once during BFS. The space complexity is O(g), where g is the number of gates, as the queue size depends on the number of gates being processed. This approach not only ensures correctness but also avoids redundant computations and additional memory usage by updating the grid in place. By combining efficiency and simplicity, this solution effectively calculates the shortest distances for all empty rooms, meeting the problem's requirements and handling edge cases seamlessly. Here, we start by importing the D class from the collections module, which will help us efficiently handle the breadth-first search, or BFS, traversal. Inside the solution class, we define the walls and gates function. The first thing we do is check if the input room's grid is empty or if it has no rows, and if that's the case, we simply return because there's nothing to process. Next, we calculate the number of rows and columns in the grid. We also initialize a queue, which will hold the positions of all the gates as we find them. Now, we loop through each cell in the grid. If a cell contains a gate, represented by the value 0, we add its coordinates to the queue. This ensures that all gates are starting points for the BFS. Finally, we define a list of directions, representing the 4 possible moves up, down, left, and right which we'll use during the BFS traversal. After this setup, we move into the BFS loop, where we process each position from the queue one by one. For each position decoded, we explore its neighbors in all four directions using the directions list. If the new position is within bounds and contains the value 214,748,3647, which indicates an empty room that hasn't been visited yet, we update its distance to be one more than the current position's distance. This ensures that we're calculating the shortest path from the nearest gate. After updating the room's value, we add this new position to the queue so that its neighbors can be processed in subsequent iterations. This BFS guarantees that all rooms are updated in layers, starting from the gates and moving outward, ensuring optimal distances are calculated efficiently. Here, we begin by importing the necessary libraries and defining the solution class along with the walls and gates method. The input is a 2D grid, represented as an integer matrix, where each cell can be a gate, a wall, or an empty room. First, we handle the edge case where the input matrix is null or empty by simply returning. Next, we determine the dimensions of the grid using the length properties of the matrix and initialize a queue to facilitate a breadth-first search, or BFS. The goal is to process all gates in the grid simultaneously, so we iterate through each cell in the matrix. If a cell contains a gate, represented by the value 0, we add its position to the queue. This ensures that all gates serve as starting points for the BFS. Additionally, we define a directions array to represent possible movements in the four cardinal directions: up, down, left, and right. This setup allows us to systematically explore neighboring cells as we expand outward from each gate. Now, we proceed with the BFS logic. While the queue is not empty, we retrieve and remove the first element, which represents the current cell's coordinates. Using these coordinates, we loop through the directions array to calculate the potential neighbors by adding the direction offsets to the current cell's position. For each neighbor, we check if it lies within the grid boundaries and if it represents an unvisited room, indicated by the value integer.max_value. If these conditions are met, we update the neighbor's value to be 1 greater than the current cell's value, effectively recording the shortest distance from the nearest gate. Finally, we add this neighbor's coordinates to the queue so that it can be processed in subsequent iterations. This process continues until all reachable rooms have been updated with their distances from the nearest gate. To solve the walls and gates problem, we use a breadth-first search, or BFS, approach. We start with an example grid where the value 21474833647 represents an empty room, -1 is a wall, and 0 is a gate. The goal is to fill each empty room with the shortest distance to a gate. First, we initialize the number of rows and columns in the grid, set up an empty queue to facilitate BFS, and locate all gate positions. In this grid, gates are at positions 0, 2, and 3, 0, so they are added to the queue. We also define 4 cardinal directions: down, right, up, and left to explore neighboring cells. Starting BFS, we process the first gate at 0, 2. Moving downward to 1, 2, we find an empty room, update its distance to 1, and add it to the queue. Similarly, moving right to 0, 3, another empty room is updated and enqueued. The other directions are either blocked by walls or out of bounds, so no further action is taken for this gate. Next, we process the second gate at 3, 0. Moving upward to 2, 0, we find an empty room, update its distance to 1, and add it to the queue. The other directions are either blocked or invalid. The BFS continues by processing the newly enqueued positions, updating distances for valid neighbors while ensuring that each empty room is reached in order of increasing distance. This process repeats until the queue is empty. Once complete, all empty rooms are filled with the shortest distance to their nearest gate. For this example, the final grid shows distances correctly updated, with values like 3 and 4 representing the shortest paths. This demonstrates how BFS ensures both correctness and efficiency. Now, consider a different case where all cells are walls. In this next example, the grid consists entirely of walls, represented by -1. After initializing the rows, columns, and an empty queue, we notice that there are no gates in the grid. Without any gates, the queue remains empty, and no BFS traversal occurs. As a result, the grid remains unchanged, with all cells still set to -1. This outcome makes sense because there are no gates to calculate distances from. Now, let's look at a simpler case where the grid contains only a single room. In the final example, The grid contains just one cell, representing a single empty room with the value 2147483647. After initializing rows, columns, and an empty queue, we again find that there are no gates in the grid. Consequently, the queue remains empty, and no BFS traversal begins. The grid remains unchanged, as there are no gates to calculate distances from. To summarize, the BFS approach efficiently calculates the shortest distance to the nearest gate for all empty rooms by processing gates first and updating neighboring cells in order of increasing distance. The algorithm runs in O(m*(n) time complexity, where m and n are the dimensions of the grid, making it both efficient and scalable. The time complexity of this problem boils down to two main operations. First, we have the initialization step, where we iterate through all the cells in the grid to locate the gates. Since the grid has m rows and n columns, this operation visits each cell exactly once, resulting in a time complexity of O(m*(n). Next, we perform a breadth-first search, or BFS, starting from all the gates simultaneously. Here, each cell is processed at most once because, after updating a cell's value, it is no longer eligible for further updates. This is ensured by the condition that checks if a cell's value is still 2147483647. Adding cells to the queue and processing them involve constant time operations, so the total time spent on BFS across all cells is also O(m*(n). When we combine these steps, the overall time complexity is O(m*(n) for initialization plus O(m*(n) for BFS, which simplifies to O(m*(n). This efficiency ensures that the algorithm scales well even for larger grids. Now, let's examine the space complexity of the solution. The primary contributor to space usage is the queue used during BFS. In the worst-case scenario, where all cells in the grid are initially 2147483647 and there's a gate in one corner, the queue could potentially hold all cells in the grid. This gives a space complexity of O(m*(n) for the queue. Aside from this, the algorithm uses a few additional variables such as the directions list and loop counters, but these require only constant space, or O(1). Since the queue dominates the space usage, the overall space complexity of the solution is O(m*(n), which, like the time complexity, scales linearly with the size of the grid. Let's break down the complexity further by considering the best, average, and worst-case scenarios. In the best case, all cells in the grid are gates. Here, the queue is initialized with all the cells, but since no BFS propagation is needed, the overall complexity remains O(m*(n) due to the initial iteration through the grid. In an average case, where there's a mix of gates, walls, and empty rooms, BFS propagates distances from the gates to all reachable cells. Even in this scenario, each cell is processed only once, so the complexity remains O(m*(n). Finally, in the worst case, when there is only one gate and all other cells are 2147483647, BFS must traverse the entire grid to update all cells. Even in this case, the complexity is O(m*(n). This consistency across all cases highlights the efficiency of the algorithm. To put things into perspective, let's compare the optimized approach to a naive one. A naive solution would involve iterating through each cell and performing a separate BFS or DFS to find the nearest gate. If there are k gates in the grid, this approach would result in a time complexity of O(k*(m*(n), which becomes significantly inefficient as the number of gates increases. In contrast, the optimized approach initializes the queue with all gates and performs BFS from all gates simultaneously. This ensures each cell is processed only once, achieving the optimal O(m*(n) time complexity. The proof lies in the algorithm's design. Each cell is visited once during BFS and added to the queue at most once. Queue operations like appending and removing elements are O(1), keeping the processing efficient. As a result, the algorithm scales linearly with the size of the grid, achieving both O(m*(n) time complexity and O(m*(n) space complexity, making it far superior to the naive approach. One of the most common mistakes in solving the walls and gates problem is not accounting for edge cases. For example, what happens if there are no gates in the grid or if all the cells are walls? These scenarios can lead to incorrect results if not considered. Always take a moment to think through extreme input cases. Another frequent issue is prematurely modifying the input grid. Overwriting the grid while processing distances can result in distorted outputs because subsequent BFS or DFS searches will rely on those altered values. To avoid this, use a separate data structure, like a visited set or queue, to track your progress. Additionally, inefficient distance calculations can be a problem. If you iterate through the grid and perform BFS or DFS for every single empty room, it becomes incredibly slow for large grids. Instead, reverse the process by starting BFS from all gates simultaneously. Lastly, there's often confusion between BFS and DFS. For this problem, BFS is the better choice because it guarantees the shortest path in an unweighted graph, whereas DFS does not provide this guarantee and can lead to incorrect results. Another key issue is failing to validate neighboring cells properly. Before processing a neighboring cell, ensure it's within the grid bounds, not a wall, and still unvisited. Skipping these checks can lead to runtime errors or incorrect results. Now, let's discuss some insights for interviews. This problem is a classic variation of the multi-source shortest path, a common graph traversal pattern in grid-based problems, and BFS is the most efficient approach to solve it. During an interview, always clarify constraints, such as whether modifying the input grid is acceptable or if you're allowed to use additional space. Additionally, demonstrate your ability to weigh time and space trade-offs. For example, BFS has a time complexity of O(m*(n), but it requires extra space for the queue. Showcasing attention to edge cases also highlights the robustness of your solution and can leave a strong impression on your interviewer. This problem is closely related to a few others on LeetCode. For instance, LeetCode 542, the 0-1 matrix problem, uses a similar BFS approach to calculate the shortest distance from 0, and LeetCode 994, rotting oranges, involves multi-source BFS for grid traversal. A more complex variation is LeetCode 317, shortest distance from all buildings, which combines these concepts but with additional challenges. Let's also look at alternative approaches. A brute force method would involve computing the distance from every empty room to all gates. However, this approach results in a time complexity of (m times n squared, which is infeasible for large grids. On the other hand, the optimal solution is the multi-source BFS approach, where you start BFS from all gates simultaneously and propagate distances to the empty rooms. This ensures a time complexity of (m*(n) and is suitable for larger grids, making it the preferred method. DFS is another potential approach, but it's not recommended for this problem. Unlike BFS, DFS is less efficient and does not guarantee the shortest path, which is critical here. Additionally, DFS can lead to stack overflow on large grids unless implemented iteratively, making it less practical. Now, when considering trade-offs between the different methods, brute force is simple but highly inefficient. Multi-source BFS strikes the best balance, offering optimal performance while requiring some additional space for the queue. DFS might be suitable for smaller grids but introduces inefficiency and stack-related risks for larger inputs. Understanding these trade-offs is crucial to choosing the most effective solution for this problem. Thank you for staying with us through this session. To summarize, we reviewed the walls and gates problem and implemented an efficient BFS solution. This problem highlights the power of grid-based traversal techniques and reinforces core problem-solving concepts. If you enjoyed this breakdown, don't forget to like, share, and subscribe. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!